Okay, in this lecture we're going to talk about a different bonding model, that one called the valence bond theory, or also called hybridization. Okay, so if we take CH4 for example, so we're going to talk about Sp3 hybridization here. So CH4 is known to be a tetrahedral molecule, right? It's known to look like that, and where the bond angles are 109.5 degrees. So in valence bond theory, it just tries to predict what the shape of the molecule looks like in 3 dimensions, but it doesn't really discuss anything at all about how are atoms actually attached to each other. So how is hydrogen actually attached to carbon? What orbitals are being used to make bonds? And so that's what valence bond theory tries to address, is how are the atoms actually attached to each other at the atomic level. So what orbitals does carbon have? It's 1s2, 2s2, 2p2. And core electrons are the 1s2. And the valence electrons, which are the ones that used to make bonds, are this 2s2, 2p2. So we're going to basically ignore the 1s electrons because they're not doing anything. It's the 2s and 2p electrons that matter. So if carbon made bonds purely from its p orbitals, so if that was py, and if that's px, and then of course it's got pz coming in and out of the plane towards you. So if it used purely p orbitals to make bonds, and then so what does hydrogen have? Hydrogen is just 1s1, so it's got a spherical orbital. So if hydrogen's orbitals overlap carbon's orbitals, so if the 1s overlapped py and px, for example, then that bond angle would be 90 degrees, since py, px, and pz are all mutually perpendicular to each other. But that does not fit experimental, because experimentally it's known that the bond angles are supposed to be 109.5. So what we want to do is come up with a new set of orbitals that carbon could use to make bonds. Okay. So if we put the orbitals in energy, in order of relative energy, so you have the 1s, the 2s, and then the 2px orbitals, so 2px, 2py, 2pz. So carbon's got 2 electrons in the 1s, 2 in the 2s, and 2 in the 2p. So what we're going to basically do is we're going to ignore these and only use the 2s and 2p electrons, and then we're going to take this electron and move it up an energy level, so that requires energy. So now 1 electron in each. And then what we're going to do is we're going to take these 4 orbitals and we're going to mix them, or just a fancy word for that is hybridize. That's what hybridize means, right? It's a mixture of different things. So we're going to mix those 4 together. So basically what we're really doing is math. We're taking the equation for the s orbital and mixing it with the equation for the px, py, and pz orbital, mixing those mathematically together and getting a new equation out. And then when we graph that, we get a different shaped orbital out. So basically we're going to take the 2s, we're going to take 2py, we're going to take 2px, and 2pz, and we're going to hybridize them. So we're going to take the 4 equations for those 4 different orbitals, mix, so we're basically doing math, but we're not going to cover the math because it's very complex. And when you mix them together, you get 4 new orbitals out, and when you graph the equation for those orbitals, they look something like this. So we'll get 4 of those. and we call those Sp3 hybrids. So basically they have a small lobe and a big lobe. Why are they called Sp3 hybrids? Because we took one of these and three of these. So we took an S and we took three P's and we mixed them together and get four new orbitals out called Sp3 hybrids. Okay, so what we want to do now is take carbon nucleus and arrange the four Sp3 hybrids around nucleus to maximize distance between them. So let's take, so one of the orbitals we'll put in that direction. So the big lobe on one side of the nucleus, a small lobe on the other side of the nucleus. We'll take another one, put it in this direction, and we'll take one with its big lobe going behind the page and its small lobe coming out towards you. And for the fourth one, its big lobe would be coming towards you, so we'll put it on a solid wedge and its dotted line to represent the small lobe going behind the nucleus. So for our practical purposes, you can ignore the small lobe. It basically doesn't do anything, it's just there. And so we had four orbitals to begin with, an S and PX, PY, PZ. Now we still have four orbitals, they're just different shaped. Okay, and so what we want to do now is attach hydrogen. So hydrogen just has an S orbital, so four hydrogens. And then each hydrogen brings one electron, and each carbon brings four electrons, four valence electrons. And so where those orbitals overlap, is a covalent bond. And so that's what we would normally just represent with a stick or with a line or a dotted line or a solid wedge to represent the three-dimensional aspect of it. So then the molecule then looks like this, right? So this stick and this stick and this stick and this stick represents the carbon's sp3 orbital overlapping with hydrogen's s orbital. So anything that's sp3 hybridized basically looks like that. So any atom basically that has four other things attached to it will be sp3 hybridized. And by things, what do I mean by things? By things I mean other atoms or lone pair electrons. So if we took a molecule like NH3 for example, it's got four things. It's got three atoms and one lone pair, so it'll be sp3 hybridized as well. So nitrogen will have, just like carbon, it would have four sp3 hybrid orbitals, arranged tetrahedrally in space. And then so nitrogen of course has got 5 valence electrons, hydrogen's got 1, so we've got 8 electrons to build the molecule. So then if we attach the hydrogens to 3 of these lobes, and then putting electrons, so nitrogen's got 5, so it's got 1 in each of, let's try to draw this better. So So nitrogen's got 5 valence electrons, so this sp3 orbital would have a lone pair in it basically. And then hydrogen brings 3 electrons, and so that would be your 80 electrons. And then of course nitrogen looks like that. So 1 lone pair and 1 sp3, and then an sp3 overlapping with s, sp3 overlapping with an s orbital, and an sp3 overlapping with an s orbital. And the same would be true for water. It's got 4 things attached. So if you modified this picture for water, you would just change N to O, and instead of having a hydrogen attached here, you would just have another sp3 orbital with another lone pair electrons attached, or in that orbital. And that is sp3 hybridization.